Hello, everybody. Welcome back to the On Centerline podcast. I am Sam Terrell, the Northwest Aeronaut on YouTube. Thank you for joining me today. Again, if you haven't found the YouTube channel, if you're listening to me on your podcast provider, check out YouTube. Look for Northwest Aeronaut. I got what I hope to be or consider a lot of great content on there, as well as all of these podcasts that you're listening to. And if you are on YouTube and haven't found the podcast, you can find it on all major podcast providers under On Centerline, the On Centerline podcast. So thanks so much for joining me today, guys. We are in the middle of our IFR, Instrument Pilot ACS breakdown, all right? Going through everything you need to know to pass your instrument pilot check ride. All right, so today is pretty much the subject that, if we were going to call one thing, if we were going to say one thing kind of embodies what being an instrument pilot is about, it's this subject. And today we're talking about weather. Now, we discussed weather pretty in depth on the private pilot ACS breakdown, and it's not really that different. Weather is weather. You just really need to have a better understanding of it when you are an instrument pilot versus just a VFR-only pilot. So today I thought I would approach it a little bit differently, and I think you guys will like this. What I did is I reached out to a few of my colleagues, a few DPEs, examiners, colleagues, and I asked them, I said, hey, what types of scenarios or things do you look for from your instrument candidates or even your CFII candidates when it comes to weather? And they were nice enough to share with me some areas that they really like to focus on, some questions they like to ask, and some scenarios they like to pose to you instrument pilot candidates. So rather than going through line by line through the ACS like we usually do, since we've done that already with the private pilot ACS, I wanted to go through these comments from my DPE colleagues, okay? So let's jump into it. Let's see here. I got a few different colleagues that I posed this question to, so I'm just going to kind of be going back and forth through some different feedback that I got. Our first one, though, he says here that he likes to ask, and this is in regards to the surface analysis or the prognostic chart, which everyone needs to be familiar with. For those of you watching on YouTube, you'll be able to see the graphic overlays that I'm putting on the screen here. And if you're not listening on YouTube, hopefully you'll get the picture through what I'm saying, but you can also check out the video on YouTube if you want to see these graphics. If we pull up a prog chart here, he says, what are all of these squiggly type black lines that we see on this surface analysis chart? Hopefully you know already that these are called isobars. And then the next question is, what is an isobar? And the answer is, and most people will tell you, that an isobar is an area of constant pressure. But what does it mean to be an area of constant pressure? Well, we can see that each isobar has a number associated with it. 1008, 1004, 1020, 1024, 1028. So one question that also might come up is, what is the difference in pressure? And these isobars are measured in millibars, okay? What's the difference in pressure from one isobar to the next? That answer, if you look here, is 4 millibars. Okay, so we can follow one isobar. This one being 1020 is going to show wherever the pressure is 1020 along the whole isobar, okay? Now, from looking at how close these isobars are to each other is going to represent a pressure gradient, okay? So what can this tell us as the pilot? What happens when these isobars are super close together versus when they're really far apart? Well, if you have a bunch of these isobars super close together, that would indicate a very steep pressure gradient. Okay? Now, just as an example, for those of you who don't quite know what I'm saying here, if you have a steep gradient, let's say we have a not so steep gradient, and I know those of you listening to this podcast aren't going to be able to see this, so I encourage you to check out the YouTube channel. But I'm laying my iPad down at just a very slight angle, and I have my Apple Pencil, and at this slight angle, I can roll my pen down the iPad. There it is. Okay? Ta-da! And of course, the more slight the angle is, the less steep, and the more shallow the angle is, the slower the pen will roll. Now, at the same time, the steeper I make it, the quicker the pen will roll. Okay? All right, so how does this relate to our isobars and what we're looking for? Well, with a steep pressure gradient, things roll, the atmosphere rolls or moves faster than when you have a more shallow pressure gradient. What in the atmosphere are we talking about when we are talking about the atmosphere rolling? Well, the atmosphere is made of air. And what do we call air that moves? We call it wind. All right, so the steeper the pressure gradient, the faster the air is going to move, and therefore the stronger the winds. When those isobars are spread out, you have a more shallow pressure gradient. It's a less of a change in pressure over distance, and therefore the winds, or the air is not going to move as fast, therefore the winds will be calmer. Okay, so isobars are a direct indication, or can give you a direct indication of what to expect for wind speed and even direction. He goes on to say, my DPE colleague, he says, how could that affect a flight over mountains? Well, we know if the isobars are close together and you are planning to fly a route that's taking you across a mountain range, you very well could encounter some mountain wave turbulence. Okay? Mountain wave turbulence is nothing to mess around with. And mountain wave turbulence, too, can cause turbulence. You don't have to be just above the mountain elevation to experience it. Mountain wave turbulence can literally go thousands and thousands of feet above the surface if the winds are strong enough and if the wind is hitting the mountain range at the right angle. Okay? We need to be particularly aware of high winds when the winds are going kind of perpendicular to the mountain range, because that's when you're really going to get a lot of the up and down motion as the winds go over the mountain range. So we need to be aware of mountain wave turbulence on those windy days. He says, what kind of clouds would you avoid over mountains with high winds? Well, you guys might be familiar with a particular type of cloud that looks like this. I'll put it on the screen for those of you listening. It looks kind of like a contact lens. Okay, a little bit of like a contact lens or just a camera lens shape. These are lenticular clouds. Lenticular clouds for a lens. We see these oftentimes on windy days. They kind of sit right over the tops of mountain peaks, and they are a direct indication of not only extremely high winds, but usually high amounts of turbulence associated with those. And we're not talking about just a few bumps. It can be very serious turbulence with that mountain wave turbulence and those lenticular clouds. So we always want to avoid flying anywhere near lenticular clouds and avoid flying over mountain ranges when we do have those high wind days. All right, he then goes on to say, what are these colored lines on the chart, on the prognostic chart? We got a blue one with little blue pyramids. We got a red one with little red half circles. Sometimes they kind of alternate. And sometimes we even get a purple one, which I don't see on this particular chart that I'm looking at, but you might get a purple one as well, or a magenta one. So these, of course, are fronts. Okay, and a front is where one air mass meets another air mass. Specifically, it's the front of the one air mass meeting the other. So he says, what are the color lines on the map? What do they mean? And then he asks about, what if there was a fast-moving cold front coming through Texas? And you know what? It just so happens on this prog chart, we kind of have a fast-moving cold front that just passed through Texas, is now over kind of Louisiana and those other southeastern states. But what might you expect if that cold front is coming down from the Rockies, from Canada, through Texas, through those southern states, meeting up with much warmer, much more saturated, moist air from the Gulf of Mexico? What might you expect to happen along that cold front? Well, if we look here at our prog chart, we see this red outline with these red lines going diagonally across it, and we can see that that is showing the chance of thunderstorms. Thunderstorms, we know the three ingredients we need for thunderstorms is unstable air, a lifting force, and moisture. Those are our three ingredients, and a cold front meeting up with a nice warm front, a nice moist warm front, lifting that air up high, creates those cumulus clouds, turning into cumulus nimbus clouds, and ultimately creating not just a thunderstorm, but a whole line of thunderstorms across that front, which we can see here on the chart. And what do we call a line of thunderstorms? We call it a squall line. So we want to be aware of those and how that might change our flight planning if we saw that a cold front or a squall line was going to be passing around the time we were planning to fly. All right, lastly, you just want to be able to look at this prognostic chart. We want to know about the pressure systems, the highs and the lows. How does air move around a high pressure system? How does it move around a low? We talked about this before, but basically, due to the Coriolis effect, air around a low pressure system is going to move counterclockwise, inward, and upward in the northern hemisphere. In the southern hemisphere, everything I'm saying is reversed, okay? But in the northern hemisphere, counterclockwise, inward, and upward for low pressure systems. For high pressure systems, downward, outward, and clockwise, okay? So, know how that works, know what each pressure system does, and then know how you can use that information to your advantage when doing your flight planning. I think we might get into that a little bit more here in a second. But let's go ahead and read some more here. I'm going to read directly. One of my colleagues in particular was very thorough, and I really appreciate his input. So I'm just going to kind of start reading from the message he sent me. And he said how he approaches evaluating weather for the instrument and the flight instructor instrument check rides is that, he sees it as you already should have a basic understanding of weather theory from your private. Hopefully you do. Okay. So on the instrument check ride, he says, I'm of course mostly interested in weather as it relates to instrument flight. As a general rule, I like to use the current/actual weather for these scenarios whenever it is interesting enough. But if the weather is too nice, then he'll have to fabricate some scenario. But one thing he says he always likes to ask about is personal minimums. Personal minimums, guys, so important, especially when it comes to IFR flying. I think we talked about back in the one of the episodes, I forget which one, but remember that go, no-go decisions are generally pretty easy as a VFR pilot. You look at the weather. If it's VFR, you go. If it's IFR, you don't go. All right. And obviously there's a gray area in there too. But certainly as a VFR pilot, if you see red for IFR or purple, magenta for low IFR, you know right there and then it's a no-go. Period. End of story. When you become an instrument pilot, That's no longer the case. Red does not any longer mean stop necessarily, unless you set that as one of your personal minimums. Okay, as an instrument-rated pilot, you can fly an approach down to minimums. Low IFR doesn't mean you can't go. So it's so important to have these personal minimums laid out, especially as a new instrument-rated pilot, because just because you've been doing all of these approaches in your training down to minimums, probably in simulated conditions with a CFI next to you, not the same as doing it in real life, in real actual conditions when you're by yourself, or even worse, when you're with a family member or a friend. Okay, so important to set personal minimums in this regard. He asks about that. Says reading weather products, icing risk and avoidance, and he tries to emphasize decision making. Okay, weather products, guys, lots of products out there. Number one, you need to make sure that the products you're looking at are approved sources. What's considered an approved source? Well, generally we get our information from the National Weather Service. Generally get our information from the National Weather Service and the National Oceanic and Atmospheric Administration, or NOAA. So no matter what source you use, you need to make sure that the information is coming from those agencies. Now, we have it pretty easy these days. We have things like, of course, aviationweather.gov. We have ForeFlight. We have Flight Service. All of these sources will give you the proper information from those two organizations. Okay, and it's nice and easy to corroborate between those sources as well. So whether it's a prognostic chart, whether it's a winds and temperatures aloft chart, whether it's a surface analysis or a graphical aviation chart, rather, lots of products, you need to make sure you know how to read all of these products. If you are going to show up for your check ride and pull up a weather briefing in ForeFlight, you need to be able to go through that weather briefing and explain what everything is. One thing I see a lot of people struggling with when it comes to, let's say, air mets. If I asked you, what is an air met? What would your answer be? Is an air met a forecast? Well, no, it's not. An air met is an advisory, and specifically it's a warning that conditions may exist. And I want you to remember those words. A warning or advisory, whichever word you want to use there, that conditions may exist. It's not saying if you see an air met for icing, you got to remember, air mets cover huge, thousands of square miles, huge areas. There's no way that they could say, yeah, if you're flying anywhere in this area, you're going to get icing, or you're going to mountain obscuration. There's going to be, all the mountains are covered. That's not what they're saying. They're just saying that if you fly in this area, somewhere in here, you might get icing if you're in the right conditions. Okay? I always relate it to this little anecdote, whatever, that if I were to go outside, and, again, we're here in the Pacific Northwest, lots of trees and wooded areas. If I were to put a sign outside that said, warning, squirrels in the area, would you expect to walk outside and just be attacked by a bunch of squirrels? Or even see a squirrel? Probably not. Now, does that make the sign invalid? No. There are squirrels in the area, and sure, you might even see one. I doubt you'll get attacked by a bunch of them, but you very well could see one. So the sign is still perfectly valid to say that, hey, there are squirrels in the area. It doesn't mean you're ever going to see them. Certainly doesn't mean they're going to be a danger to you. Okay, so air mets are kind of like that. They're very general, and in order to know whether or not what the air met is warning you to is going to be an issue, you need to corroborate other sources of information to see. For instance, like if it's an icing air met, okay, first of all, where's the freezing level? Are there going to be clouds along your route that you're going to be in at or above that freezing level? Okay, and then you can get a clear idea of whether or not icing is going to be an issue for you. All right, let's see what else he says here. Talking about icing risk and avoidance. So first of all, when it comes to icing, you need to know the 3 different types. In general, we have clear icing, we have rime icing, and we have mixed icing. Honestly, I've never understood why they create a whole third type based on a combination of the first 2, but they do. Okay, so rime, clear, and mixed. And we need to know what weather sources we can look at to know the risk or the probability of us encountering ice. So for these things, of course, we're going to look at our winds and temps aloft. That'll give you an idea of where the freezing level is. We also want to look at the icing forecast. There's an actual icing forecast that you can look at in either ForeFlight or, of course, on aviationweather.gov that shows you the probability and intensity of icing at different altitudes. Okay? So we want to know about that. And as we discussed earlier, you want to know the effect that icing has on your airplane, what you should and should not do if you suspect or know that you are accumulating airframe icing. That's the other thing. There's different types of icing, right? You got airframe icing. You have induction system icing, carburetor icing. You can get icing on the ground or in the air. Okay, again, icing on the ground would show itself in the form of frost, right? Frost on the aircraft is airframe icing. We generally don't want to use flaps if we have airframe icing. One thing that you need to be kind of in tune with is what are the signs that you are accumulating airframe icing? Where would you look for it? What would be some indications that you are accumulating it? I like to look, of course, we talk about looking at the small surfaces along the airframe, antennas, if you can see them, and along the struts or things like that on the airframe. But I like looking on the tire. The tire can be a good indication because it's black, so it kind of contrasts the white of the ice or snow. And then, of course, you want to listen to your radios. We can't really see our antennas usually, but if you are accumulating ice on your antennas, you will often get radio static. So if you're flying along and all of a sudden this static comes along out of nowhere and you're having a hard time communicating, that could be a good indication that you might be accumulating some ice on those radio antennas. Okay, so be in tune with things like that. Okay, let's take a look at our next paragraph here. Instrument check guy says either using actual weather or else he'll give the departure weather scenario. He'll give a scenario like ceiling is 500 feet, visibility is unrestricted, winds are 200 at 15 knots. And he'll ask them if and how they would depart from the particular airport. Things that he's looking for would be, do you understand the legal requirements for an IFR departure? Do you select an appropriate runway for the departure and compare your aircraft performance against the takeoff minimums for that departure procedure? Do you consider or incorporate personal minimums in the go, no go decision? And he goes on to say one specific scenario that he really likes to use, and I'm going to put this up on the screen for those of you watching on YouTube. He likes to go to the Tillamook Airport, which is here in Oregon, not too far from us here in Hillsboro, just off to the west on the coast. And he likes pulling up the FETUJ 3 obstacle departure. This is the obstacle departure procedures, the ODP, out of the Tillamook Airport. Let's go ahead and get this up on the screen here. All right, the FETUJ 3 obstacle departure. This is an RNAV departure. And he says he likes posing this as a scenario. And he'll give the scenario as follows. He'll say in a 172, if I give them, the wind will be 130 at 10 to 15 knots. We'll say 130 at 10 knots. And, of course, the rest of the minimums could be anything, ceilings at 500, whatever. All right, so winds are 130 at 10 to 15 knots. Let's take a look at this departure procedure. This is the FETUJ 3 departure. Takeoff minimums, runways 1319, NA. First of all, what does NA stand for? A lot of people say not applicable. Some people say not available. Okay. There's only one thing that NA stands for on an approach plate or departure procedure or arrival, and that is not authorized. Okay. Not authorized. So takeoff minimums for 113 and 19er are not authorized. Let's see here. It says runway 31 has a standard takeoff minimum with a minimum climb of 395 feet per nautical mile up to 5,000 feet. So you are not able to take off and do this departure procedure on any runway except runway 31. And yet he said what the winds are 130 at 10 to 15, 10 gusting 15. If we're taking off on 3-1, that means we're going to have a 10 to 15 knot tailwind. Let's look at our takeoff obstacle notes. It says runway 31, there's a bush 76 feet from the departure end of the runway, 283 feet right of centerline, 3 feet AGL, and 32 feet MSL. Okay. Watch out for that bush, guys. It's a doozy. There's a fence 111 feet from the departure end of the runway. There's a monument 1,275 feet from the departure end of the runway. Let's see. There's a pole. There's some trees. Okay. So those are just some takeoff to obstacle notes. But the big thing is, it says for the departure route description, it says climb on a heading of 316. So basically straight out from runway 31 to 540 feet. Then climb to 5,000 feet or as assigned by ATC, direct to FETUJ, which is the intersection or the waypoint. Cross FETUJ at or above 5,000. All right. The procedure's simple enough. You're basically just flying straight out on runway 31. However, based on those takeoff minimums, we need to be able to maintain a standard takeoff minimum with a minimum climb of 395 feet per nautical mile. First of all, when it says standard, what does that mean? Well, standard for us in a 172 having less than 2 engines, or, well, 2 or less engines, it means that we need at least 1 mile of visibility, and we need to maintain at least 200 feet per nautical mile on our climb. So here it says standard, except you need a minimum climb of 395 feet per nautical mile. So basically it's saying you need 1 mile visibility, which technically doesn't apply to Part 91. Doesn't mean you don't want to adhere to it, though. Okay, so standard visibility, but the climb needs to be 395 feet per nautical mile. If we look at if we go to our documents here, and we look up our digital terminal procedure supplement, where we can pull up our graph, our instrument takeoff or approach procedures. This is our rate of climb / descent table. We can look up, let's say we have a ground speed. Well, we got to figure out our ground speed, right? So it says in the 172, we're going to be climbing out at VY. Let's call it 75 knots. We're at sea level. So 75 knots indicated is mostly going to be 75 knots true, and until we get a little higher at least. So 75 knots is what we're doing through the air. Add, let's say worst case scenario, 15 knots of tailwind to that. Now we're going 90. 90 knots over the ground. And we know we are going to need that 395 feet per nautical mile all the way up to 5,000 feet. So if we look here at our graph and we look at, this is our feet per nautical mile column. We go down to 395, which we're just going to round up to 400. 400 feet per nautical mile at 90 knots. Right here is this second column here. We need 600 feet per minute of climb all the way up to 5,000 feet. Now, can you do that on 172? Depends. What 172 are you in? Are you in a older 172 with 150 horsepower? Or are you in a newer one with 180 horsepower? Are you fully loaded at max gross weight? Is it just you in the airplane and fairly light? Lots of variables to consider there. But can you hold 600 feet per minute on average all the way up to 5,000 feet? It's going to be tough. It's going to be tough. So that's the type of thing you need to be able to think about. And ideally, have personal minimums around. You should have personal minimums for the amount of tailwind you are comfortable taking off with, number one, or landing with. You should have personal minimums for what type of conditions you are willing to depart in. Again, just because it's legal for you to depart, and just because maybe your airplane might be able to do it from a performance standpoint, does that mean that you should be doing it as a relatively low-time instrument pilot? All right, so these are the things he wants to hear about. Let's see what he says next. He says, just to sum that up real quick, or just to wrap that up, he says, now the student has to decide how comfortable they are departing with a tailwind, and their new ground speed might put them under the required climb gradient. All right, so that's what he says about that. All right, he goes on to say that for the arrival/alternate planning, my scenarios are pretty straightforward. Some of the common errors he sees is just people not actually knowing how to read the times in a TAF. Either they have trouble decoding Zulu time, or they can't figure out which lines of the TAF apply to their quote-unquote 1 hour before and 1 hour after. You know, TAFs can be hard to use in that way when we're talking about our alternate minimums. Needing to know what the forecast weather is at your destination 1 hour before to 1 hour after your estimated time of arrival. Well, TAFs aren't set up that way. They might be at 4 hour increments. So in that case, if you're looking at the TAF, you kind of have to figure out how your estimated time of arrival falls into one or two of those lines of the TAF. But there is a better way that I personally like, and that's using aviationweather.gov, using the GFA tool. If we look here, I'm going to pull it up. Give me 1 second. Okay, so what you see on the screen here right now, for those of you watching on YouTube, this is the ceiling and visibility GFA graphical aviation forecast tool. And you can see along the bottom here that we actually have Zulu time by the hour. We can go forward or back 1 hour at a time and see how the visibility and ceiling change from hour to hour. So especially if perhaps you're going to an airport that doesn't have weather reporting on field, this is a great tool to kind of see in the general area, because I can zoom in and take a look. What is the weather kind of supposed to be forecast for around my time? I can go from 0400 Zulu. If I'm planning to arrive at 0500 Zulu, then be 0400, looks good. All the way to 0600, looks good. I might not need an alternate in that case. But this is the tool I recommend for using when you are deciding whether or not you need an alternate and looking at that 1 hour before to 1 hour after. All right, guys, let's go on here. He says, particularly for CFII candidates, One scenario he likes is a pretty common one for us here in the Pacific Northwest and in the Willamette Valley, but he says you want to do an instrument training flight with a student. The weather is currently a solid 500 feet overcast. Okay, not uncommon here this time of year. You have multiple pi reps indicating that the tops are around 3,000 feet, which is a great day. I mean, those are really low tops and easy enough to get up on top there, even just to do a VFR flight. Sometimes I'll even take private students or, students working just on their private certificate. And I'll file IFR, get us up on top so we can do all of our maneuvers. It's a great little intro for the private student to the instrument world, allows them to kind of get a new appreciation, not just for aviation, but for hopefully inspiring them to get their instrument rating down the line. So anyway, 3,000 foot tops, and then it's clear above. However, the temperature is 2 degrees Celsius on the ground. Are you going to go or are you going to cancel? Well, if we look at our standard lapse rate and temperature, 2 degrees Celsius per 1,000 feet. Well, if it's 2 degrees on the ground, that means by 1,000 feet, we're going to be at 0. That's your freezing level. And then 2,000 feet, -2. By the time we get to 3,000 feet at the top of the clouds, we're going to be at -4. And by the way, little tidbit, if you're looking at the base of the clouds through the middle to the top, it's the top of the clouds you generally have the most chance of getting icing, all right, and the most severe icing. So from -4 degrees by the time you break out of the clouds, and yeah, it's clear on top, but that just because you're out of the clouds up above 3,000 feet, temperatures are still cold, right? So if you accumulate any amount of ice on your way up through those clouds, it's not going to just go away once you're up there. You're going to be flying around with it, and then you're going to probably accumulate more on the way back down. So do you cancel or do you go? Do you go or no go? He says that it's a good scenario because it's a scenario in which it may or may not technically be known icing. Okay, and of course, in a Cessna 172 or any other equivalent trainer, they are not going to be certified for flight into known icing. So whether, even if this is not considered technically flight into known icing, he says that this is one of the scenarios that almost everybody has a good enough sense when they're just sitting here in a check ride environment to say, no, I'm not going to go. Too risky, not worth it, whatever. Okay. And yet, he goes on to say that when he looks at flight radar on those exact days, when those days come around and he's looking on FlightAware or whatever, there's tons of people out there shooting approaches. So it's one of those things where, it's a very slippery slope and it's easy enough to kind of sit back completely objectively and say, no, that's a bad idea. But when the day comes and you've got the student waiting, wanting to get out, maybe it's been 2 or 3 weeks since you last flew because, again, weather hasn't been great. And this day is looking, halfway decent. If only we could get above those clouds. The student wants to go. Your bank account is kind of hurting. The pressure of all those external pressures, all those things, tend to make that scenario look not that threatening. And yet, it certainly can be. All right, guys, almost done here. Lastly, I want to go through just a few other notes from one of my colleagues as well. Some things that he likes to talk about. Yeah, he talks about how fronts affect the weather and how you'd use them for flight planning. We kind of talked about fronts, specifically pressure systems, and we talked about how air moves around pressure systems, right? So ideally, up here in the northern hemisphere, if we're flying from west to east, okay, I know it's backwards, west to east for you looking at me here on YouTube, knowing that air circulates clockwise around a high pressure system and counterclockwise around a low pressure system, Ideally, if there were two pressure systems, one above each other and one below, we would want a low pressure system above us. And when I say above us, I mean north of us, and a high pressure system to the south, so that the wind, we could fly right between those two, going this way, right between those two systems to give us a good tailwind on our trip. Better fuel economy, less time en route, all good things there. So that's just one example of how you might use pressure systems, in this case, in your flight planning. He asks about when to turn pitot heat on. One critical thing to remember, guys, when it comes to icing and the very small tools we have in our trainers to combat icing is you need to know the difference between anti-icing devices and de-icing. Anti-icing is a preventative. De-icing is to get rid of existing ice. The majority of planes and the majority of tools on the majority of planes are all anti-icing tools. So things like our pitot heat is an anti-ice device. It needs to be used before you accumulate any ice. And ideally, of course, we're not going to accumulate any ice because we're not supposed to be in those conditions. But I personally turn on pitot heat anytime I'm in visible moisture and the outside air temperature is below 40 degrees Fahrenheit or 5 degrees Celsius. Okay, so if we're flying through the clouds at 2 degrees Celsius, 3 degrees, or 35, 36, 7 Fahrenheit, that pitot heat's going to be on. Okay. He specifically also asked about the type of icing that can occur on the ground. Again, frost. Okay, frost on the ground. He asked about fog. What type of fog do we get here in our little valley in the Pacific Northwest? What type of fog do we get on the coast? You want to know the kind of main types of fog. Got your radiation fog, got your steam fog, your advection fog, your upslope fog, okay? Your precipitation fog. You want to know the different types and generally where and under what conditions you would find them. And you especially want to know if you live in an environment where fog is a normal occurrence. You want to know what type of fog you get in your area, okay? Here in the Willamette Valley, we often get radiation fog on those cool, calm nights, cool, calm mornings. All right, guys, so to wrap up this section, we're just going to look at the skills section straight out of the ACS. It says the applicant exhibits the skill to use available aviation weather resources to obtain an adequate weather briefing, analyze the implications of at least 3 of the of the conditions listed in K3A through K3L. Okay, and those are all the things up top, talking about wind, temperature, moisture, weather systems, clouds, turbulence, thunderstorms, all these things, right? The next skill is to correlate weather information to make a go, no-go decision. And lastly, it says determine whether an alternate airport is required and, if required, whether the selected alternate meets regulatory requirements. So once again, this is something that I see a lot of confusion on. We talk about whether an alternate is required. Then we talk about alternate minimums. And we have standard alternate minimums and we have non-standard alternate minimums. So first of all, how do you know whether an alternate is required? Well, it's always required unless you can use your 1, 2, 3 rule, unless 1 hour before your ETA to 1 hour after your ETA, the forecast or the weather is forecast to be at least 2,000 foot ceilings, 3 statute miles visibility or better. So then you have to look at, okay, well, what if my weather is not that good? So we need to file an alternate. How do I know if I can file a certain airport as an alternate? We have to look at, among other things, our alternate minimums. If the airport has a precision approach procedure that we can use, remember a precision approach procedure is basically an ILS for our our, and when I say our, I mean in the flight training environment, the GA environment, there's not usually going to be many other precision approaches out there other than an ILS. So an ILS, any GPS approach, any RNAV approach is considered non-precision. So remember that. So if it has an ILS that you're planning to use and that's available to be used, then the alternate minimums at the estimated time of arrival at your alternate need to be minimum 600-foot ceilings and 2 miles of visibility. If it only has non-precision approaches available, then the weather needs to be at minimum 800-foot ceilings and 2 statute miles visibility. Those are our standard alternate minimums for Part 91. However, things are rarely standard, guys. How do we know if a certain airport or a certain approach has non-standard alternate minimums? Well, if we look at one of our approach plates, put it up on the screen here, let's just pull up any approach plate. Looks like I'm going to pull up one for, let's look at Corvallis Airport, Corvallis, Oregon. And let's look at the ILS there. How about that? Oh, what's this we see in the top left corner? We see an upside down triangle with a T in it, and then a triangle below it with an A in it. This is in the notes section. That A and that T, but that A tells you that there are non-standard alternate minimums if you're planning to use this approach for this airport as an alternate. The T tells you that there's non-standard takeoff minimums. So where do we find these non-standard alternate minimums? Well, if we go to our airport here, we can look up at Corvallis. We can go to procedures. We can go to arrival and look at alternate minimums. And it says at Corvallis that the ILS or localizer, runway 17, and it says there's a little one there. And if we look down below, 1 says that localizer category Delta, category D, the minimums are 900 feet ceilings, 900-foot ceilings, and 2.5 miles visibility. Now, does that change anything for us? No, because our aircraft are not category D. We are typically category A, possibly category B, depending on what plane you're in. But we're not category D. So this wouldn't apply to us. And therefore, our alternate minimums for this approach at this airport are actually going to be standard. So we would just need to have, at minimum, 600-foot ceilings and 2 miles visibility forecasts for our estimated time of arrival at this airport as our alternate, okay? But that's how we would figure out what the alternate minimums are if they are non-standard, okay? All right, guys. Well, you know what? I think that will about do it for this episode. I hope you kind of like this format. I thought it would be really useful to get some insight from my colleagues, the people who are out there doing these check rides, maybe even a certain DP that you might be using for a check ride in the future. Okay, won't tell you who they are, but these are the types of things the examiners are looking for. All right, if you want to dive in deeper with all this weather stuff, go back and listen to my private pilot ACS breakdown on weather. It's 2 episodes. It was so much information, I had to break it up into 2 episodes. So you can scroll back in history and find it there. It's not on YouTube because I was not doing video podcasts at the time of those recordings. So it's only going to be on a podcast provider, either Spotify or Apple Podcasts or anywhere else you get your podcasts. All right. Hey, I really appreciate you guys spending time with me today, and we will see you next time on Centerline.